just a little bit more to help you understand the behavior of exponential and log graphs. So right here we have the function f of x equals 3 times 2 to the x, which is an increasing exponential function. And you can see I've got the points labeled that are the same points I've labeled here in this table. What I want you to notice is how this growth is occurring. First of all, I want you to notice one key point here, the 0, 3. When x equals 0, y equals 3. That point is found right here in the equation, because that coefficient is always going to be the y-intercept, because when x is 0, it's going to be 3 times 2 to the 0. Oops, let me write that down. Because 3 times 2 to the 0 equals 3. Okay? Now, the other number, the 2, is the rate of change. Now what I want you to notice here with the y values, 0.75, 1.5, 3, 6, 12, they are doubling every time, which is why this graph grows so quickly. The x values are just going up by 1, but the y values are doubling each time. So we have 0.75, 1.5, 3, 6, 12, then the next one's going to be 24, and then 48. So we see that this is just going up by 1 every time, plus 1, plus 1. But this is going up times 2, times 2, times 2. So when you see that pattern, the rate of change is multiply by 2. That's exponential. Now I want you to compare that to a linear graph. In a linear graph, we have this number here is the y-intercept. Okay, so I should label that 3 there is the y-intercept for the exponential graph. And here, this is the y-intercept. Man, my pen's just not writing nicely for me today. So we see the y-intercept 0, 3. This number 2 is also a rate of change for the linear function, but when we talk about rate of change with a linear function, we're not talking about multiplying by 2, we're talking about adding 2. So you notice here that in the x value, in the x column, we're going up by 1 each time, but in the y column, we're going up by 2. We're adding 2 each time. So this would be 9, this would be 11. So when you see an addition pattern in the y column, in both the x and the y column, that's linear. When you see an addition multiplication pattern, like that's exponential. Now, the next thing I want to take a look at is when we use e as a base. So I just want you to think about e. We already know that if I have y equals a b to the x, and we have b is greater than 1, we have growth. And if we have b is less than 1, we have decay or decreasing function. So when we look at e, we have to remember that e itself is 2.71828. So just using base e is a growth function. So here we have the basic e to the x is this, do I have just e to the x? Nope, I don't have just e to the first on any of these. I have the different x. Yeah, I do. Here's the e to the x. So here's an e to the x graph. It's just growing. They all have a coefficient of 2 that I put on there. But if you look at e to the 1.5 and e to the 0.4, both are still greater than 1 in the base. So any time that this exponent, k, is greater than 0, we have a growth function because we have the base is greater than 0. Now e to the 0 is just 1. This is linear. This is not even exponential, because if we're only if the base is 1, then we're multiplying by 1 every time. It's not going to grow. It's not doubling or tripling or whatever. If we have the base, or if we have the exponent here k greater than or less than 0, sorry, if k is less than 0, then we see that our base, now on your notes, your original notes, this number might not be there. It might just say e to the negative 2, so change that if you need to. This has a base less than 0, so this is a decay function. So you can see here, the red graphs, this is e to the 1x, this is e to the 0.4x, this blue one is e to the 1.5x. So those are all growth. The green one is the one that is e to the negative 2x. So that's the one that's going down. Okay, lastly, I want to look at log graphs. How do we tell how flat the graph is? So notice they all have a they all have the asymptote on the y-axis. They all of these graphs go through the point 1, 0 because any base log of 1 is 0 unless there's a coefficient in the front. But they grow at different rates. And what I want you to notice, this is base 10. Actually, let me color code them. This is base 10. This one is the natural log, so this is base E, which is 2.71828. And then this third one is base 2. So notice the higher the base, the flatter the log graph is. So the higher the base, the flatter the log graph is. So that's really all you need to know, a little extra information about logs and exponential graphs. Just to summarize too, the higher the base for the log graph, the flatter it gets. The higher the base for an exponential graph, the steeper it gets. Because remember, they are inverses of each other. All right? Remember that if this is my log graph and it's getting very steep, then this is my exponential graph. My log graph has to get really flat. If my exponential graph is not as steep, then my log graph has to be steeper because they are inverses of each other. Okay, so just remember those are inverses of each other.